2023 Electric and Electronic Technology class. Today, I will present the topic on fundamental of electricity, electricity in the early days. The first documentation in the history of electricity dates all the way back to 500 BC when Thales of Miletus discovered static electricity by rubbing fur on amber, but it was not until 2000 years later, in the 1600s, that English physician and physicist William Gilbert published the first theories about electricity in his book, De Magnet. The next major text about electricity, experiments and notes about the mechanical origin or production of electricity was published in 1675 by English chemist and physicist Robert William Boyle. The exploration of electricity went up a notch during the next century, though when things started heating up, in the early 1700s. Decades before Franklin's kite, English scientist Francis Hauksbee made a glass ball that glowed when rubbed while experimenting with electrical attraction and repulsion. The glow was bright enough to read by, and this discovery would eventually lead to neon lighting a few centuries later. Fast forward to September 1882, when a house in Appleton, Wisconsin became the first American home to be powered by hydroelectricity. The station that powered the home used the direct current (DC) system developed by Thomas Edison. Over the next several years, the direct current versus alternating current (AC) debate captured attention, as Thomas Edison and George Westinghouse, who championed AC, competed for contracts. The war of the currents. Long before electric power in homes became mainstream, the standard form of electricity in the United States was the DC system that Edison developed through General Electric. Nikola Tesla, a student of Edison, believed that AC was a better option because, with the use of transformers, power could be converted to higher or lower voltages much easier and more efficiently. Edison argued, through what some refer to as a misinformation campaign, that AC was far more dangerous. This battle peaked in 1893 at the Chicago World's Fair when General Electric lost its bid to power the fair to George Westinghouse, who was using Tesla's AC system. Eventually, because it was cheaper to distribute and could supply power to larger areas, AC became the new standard for electricity in the U.S. The evolution of wiring and electrical components. In the earliest days of home electrification, electricity was often carried place to place by bare copper wires with minimal cotton insulation. Sockets, switch handles, and fuse blocks were made of wood. There were no voltage regulators and lights would dim and brighten in response to demand placed on the electrical grid. From about 1890 to 1910, knob and tube wiring were used for electric installation. In this early setup, hot wires and neutral wires were run separately and were insulated using rubberized cloth, which degraded over time. From the 1920s to the 1940s, flexible armored cable, which offered some protection from wire damage, became commonplace. During the 1940s, electricians began using metal conduit, in which several insulated wires were enclosed in rigid metal tubes. During these years, the potential for danger was much higher than it is today because wires were not grounded. If one of the hot wires became damaged or some other mishap caused the electrical current to escape the wiring pathways, fire or severe electrical shock was often the result. After 1965, grounded wires, which direct stray electrical current back into the ground, created a safer environment for homeowners. Most modern homes also have circuit breakers that immediately shut off power if they sense an overload, providing additional safeguards. Electricity in the modern era. Initially, electricity was used primarily for lighting, but as appliances like vacuum cleaners, refrigerators, and washing machines became more popular starting in the 1950s, demand for electricity grew by leaps and bounds. With today's myriad appliances and electronic devices, it is essential to have wiring and components that can handle the heavy load required to power our modern lives. As we settle into the 21st century, electricity continues to evolve, yet innovations, at least when it comes to our sources of power, have come more slowly. Coal, petroleum, and natural gas have been our primary sources of electrical production since the early 20th century, and alternating current still reigns. But there are changes underway. The future of electricity. According to the Center for Climate and Energy Solutions, renewable energy is the fastest growing source of electricity in the United States. increasing 67% from 2000 to 2016. Eco-conscious entrepreneurs are committed to the transition from fossil fuels to renewable electricity, which includes not only wind and solar, but also a renewed focus on hydroelectric power. As technology improves over the next few decades, a transition to renewable power sources as our primary producers of electricity is likely. And, as our appliances, and our homes, get smarter, the demand for electricity and new innovations will continue to grow. In addition, direct current has been making a comeback. LED and computers use DC, and engineers have learned that DC may be more efficient than AC when transmitting millions of volts over large regions. New DC transformers can convert from low to very high voltages just like traditional transformers do with AC. Increased use of electric cars, which operate on DC power, will also push the demand for DC. The International Energy Agency projects that the number of electric cars on the road worldwide will expand from 3 million in 2017 to 125 million by 2030. Finally, using DC power allows for easy integration of wind and solar energy into the electrical grid. Electricity basics. When beginning to explore the world of electricity and electronics, it is vital to start by understanding the basics of voltage, current, and resistance. These are the three basic building blocks required to manipulate and utilize electricity. At first, these concepts can be difficult to understand because we cannot see them. One cannot see with the naked eye the energy flowing through a wire or the voltage of a battery sitting on a table. Even the lightning in the sky, while visible, is not truly the energy exchange happening from the clouds to the earth, but a reaction in the air to the energy passing through it. To detect this energy transfer, we must use measurement tools such as multimeters, spectrum analyzers, and oscilloscopes to visualize what is happening with the charge in a system. Safety practices. Effective safety habits are necessary to succeed in the electronics field. Practicing good safety habits promotes a safe work environment. Everyone needs to be aware of and support a safe work environment. A primary concern in the field of electronics is electrical shock, which is the passage of current through the body. Current can flow through the body just as it does through an electrical circuit. How much current flows depends on these factors. Body resistance is high if the skin is dry and there are no cuts or abrasions at the point of electrical contact. This results in little current flow with only a mild shock. Body resistance is low if the skin is moist. This results in a high current flow, and if the current flow is through the chest region, the heart can receive a lethal dose of current. The heart may go into fibrillation and breathing may be stopped. Figure 2. Small amounts of current through the body can be dangerous to one's health. Large amounts of current through the body can be fatal. A shock of 1 to 20 milliamperes can cause a painful sensation. At a shock of approximately 20 to 30 milliamperes, breathing stops. A shock above 100 milliamperes results in electrocution. The work environment should be reviewed to identify problem areas. Maintaining a safe work environment is easy when you observe the following guidelines. 1. Keep the work area neat and orderly. 2. Be alert and attentive at all times. 3. Know the correct operation and safety procedures of test equipment, tools, and machinery. 4. If an accident occurs, know what action to take. Personal safety when working with electricity requires the following. Work with one hand in your back pocket or behind your back when working on live circuits. This technique avoids a complete path for current flow that passes through the heart region. Use an isolation transformer when working on AC-powered equipment. The transformer isolates the powered equipment from the power source. Make sure all capacitors are discharged before beginning troubleshooting. Use a capacitor discharge tool to discharge the capacitor. Use grounded line cords and polarized plugs with AC-operated equipment in circuits. They help to reduce the danger from hot chassis. Keep hands off live circuits. Test all circuits with a voltmeter or test lamp before working on them. Before handling toxic and hazardous chemicals, read the Material Safety Data Sheet, MSDS, to know the best protection and first aid procedures in case of emergency. When around these types of chemicals, be concerned about inhaling vapors, swallowing liquids, acid burns on the skin, contact with the eyes, and danger of fire and explosions. Follow these guidelines to minimize risk. Read the labels of all chemicals being used, paying special attention to the printed warnings. Work in well-ventilated areas, especially when working with paint and chemical sprays. Wear safety glasses when working with hazardous chemicals. Wear rubber gloves when working with acids and acid solutions. Use tongs or rubber gloves when placing or removing printed circuit boards from the acid solution. Clean all tools that contact hazardous chemicals in case anyone accidentally touches them. Safety is the #1 priority when soldering. Always follow these safety guidelines. 1. Always wear safety glasses when soldering or cutting leads. When clipping leads on the printed circuit boards, flying leads can be an eye hazard. When clipping leads, aim down and away from the face and anyone close. 2. Never touch the soldering iron tip or heating element. Only pick up the iron by the handle. Never change the tip when the iron is hot. 3. Beware of fingers slipping over the iron handle and contacting the heating element. 4. Beware of pressing the soldering iron too hard against the leads when heating. The soldering iron may slip. 5. Beware of molten solder dripping from the connection. Cotton and wool clothing are the safest to wear when soldering. Many synthetics melt on the skin if molten solder gets splashed on them, causing a greater burn. 6. Use care when handling printed circuit boards. Leads can cut or puncture the skin. Always have cuts or punctures cleaned and treated immediately. 7. Avoid breathing in flux fumes when soldering. 8. Cleaning solvents dry out the skin. Avoid breathing the vapors. 9. Wash hands before eating or drinking. The lead from the solder remaining on the hands can be ingested with food. Certain components used on printed circuit boards can be damaged by static electricity referred to as electrostatic discharge, ESD. These static charges are created when non-conductive materials, such as plastic from bags or synthetic materials from clothing, are separated. These charges can be induced on a conductor, such as skin, and are delivered in the form of a spark that passes to another conductor. By touching a printed circuit board or semiconductor device, a static discharge can be delivered through it that may damage a sensitive component or device. Most static charges that can damage a printed circuit board component or semiconductor device are too weak to feel, less than 3000 volts. Most components of printed circuit board assemblies have warnings, such as the label shown in figure, printed on them, noting that they are sensitive to damage by static electricity. Keep in mind that just because a component does not have a symbol or a label does not mean it is not ESD sensitive. The following protective guidelines help to prevent damage to components. Keep sensitive components enclosed in anti-static bags, boxes, or wraps when not working on them. Remove sensitive components from their protective wrapping only when in the anti-static work area. Keep anti-static workstations free of static generating materials such as styrofoam, plastic desoldering tools, plastic notebook folders, combs, and so on. Electrical charge. Electricity is the movement of electrons. Electrons create charge, which we can harness to do work. Your light bulb, your stereo, your phone, etc., are all harnessing the movement of the electrons to do work. They all operate using the same basic power source, the movement of electrons. The three basic principles for this tutorial can be explained using electrons, or more specifically, the charge they create. Voltage is the difference in charge between 2 points. Current is the rate at which charge is flowing. Resistance is a material's tendency to resist the flow of charge, current. So, when we talk about these values, we are really describing the movement of charge, and thus, the behavior of electrons. A circuit is a closed loop that allows charge to move from one place to another. Components in the circuit allow us to control this charge and use it to do work. Georg Ohm was a Bavarian scientist who studied electricity. Ohm starts by describing a unit of resistance that is defined by current and voltage. So, let us start with voltage and go from there. Voltage. We define voltage as the amount of potential energy between 2 points on a circuit. One point has more charge than another. This difference in charge between the 2 points is called voltage. It is measured in volts, which, technically, is the potential energy difference between 2 points that will impart 1 joule of energy per coulomb of charge that passes through it. The unit volt is named after the Italian physicist Alessandro Volta, who invented what is considered the first chemical battery. Voltage is represented in equations and schematics by the letter V, when describing voltage, current, and resistance. A common analogy is a water tank. In this analogy, charge is represented by the water amount, voltage is represented by the water pressure, and current is represented by the water flow. So, for this analogy, remember, water equals charge, pressure equals voltage, flow equals current. Consider a water tank at a certain height above the ground and figure. At the bottom of this tank there is a hose. The pressure at the end of the hose can represent voltage. The water in the tank represents charge. The more water in the tank, the higher the charge. The more pressure is measured at the end of the hose. We can think of this tank as a battery, a place where we store a certain amount of energy and then release it. If we drain our tank a certain amount, the pressure created at the end of the hose goes down. We can think of this as decreasing voltage, like when a flashlight gets dimmer as the batteries run down. There is also a decrease in the amount of water that will flow through the hose. Less pressure means less water is flowing, which brings us to current. We can think of the amount of water flowing through the hose from the tank as current. The higher the pressure, the higher the flow, and vice versa. With water, we would measure the volume of the water flowing through the hose over a certain period. With electricity, we measure the amount of charge flowing through the circuit over a period. Current is measured in amperes, usually just referred to as amps. An ampere is defined as 6.241 by 10 power 18 electrons, 1 coulomb per second passing through a point in a circuit. Amps are represented in equations by the letter I. Let us say now that we have 2 tanks in figure, each with a hose coming from the bottom. Each tank has the exact same amount of water, but the hose on one tank is narrower than the hose on the other. We measure the same amount of pressure at the end of either hose. But when the water begins to flow, the flow rate of the water in the tank with the narrower hose will be less than the flow rate of the water in the tank with the wider hose. In electrical terms, the current through the narrower hose is less than the current through the wider hose. If we want the flow to be the same through both hoses, we must increase the amount of water, charge, in the tank with the narrower hose. This increases the pressure, voltage, at the end of the narrower hose, pushing more water through the tank. This is analogous to an increase in voltage that causes an increase in current, resistance. Now we are starting to see the relationship between voltage and current. But there is a third factor to be considered here: the width of the hose. In this analogy, the width of the hose is the resistance. This means we need to add another term to our model. Water equals charge, measured in coulombs. Pressure equals voltage, measured in volts. Flow equals current, measured in amperes, or amps for short. Hose width equals resistance. Consider again our 2 water tanks in previous figure, one with a narrow pipe and one with a wide pipe. It stands to reason that we cannot fit as much volume through a narrow pipe than a wider one at the same pressure. This is resistance. The narrow pipe resists the flow of water through it even though the water is at the same pressure as the tank with a wider pipe, as in this figure. In electrical terms, this is represented by 2 circuits with equal voltages and different resistances. The circuit with the higher resistance will allow less charge to flow, meaning the circuit with higher resistance has less current flowing through it. This brings us back to Georg Ohm. Ohm defines the unit of resistance of 1 ohm as the resistance between 2 points in a conductor where the application of 1 volt will push 1 ampere, or 6.241 by 10 power by 18 electrons. This value is usually represented in schematics with the Greek letter ohms, which is called omega, and pronounced ohm. That is it for today.